Hello and welcome back to CMOS radio frequency integrated circuits. So, we are now in the 11th module and we will be discussing frequency synthesis. As part of today's lecture, we are going to talk about phase locked loop basics. In the last class, I kind of tried to motivate the need for something. So, we want a pure frequency, we can't tolerate any phase noise. We need this frequency to be agile and accurate. Now, as far as the pure frequency part goes and as far as accuracy goes, quartz crystals are very good. They are not as good as atomic clocks, but they are very good. I can further use some sort of synchronization technique on top of the quartz crystal to be as good as an atomic clock, but they are very good. I like quartz crystals as far as pure frequency is concerned, as far as the accuracy of the frequency is concerned. As far as agility is concerned, the voltage controlled oscillator is very good. It is agile, it can move around, it can change frequencies, of course with no knowledge what that frequency is, right. There is huge error in what you designed and what you get. There could be 20% error. You might want a capacitance of 1 picofarad, instead you might get 1.2 picofarad. You do not know what you are getting. You are getting some approximate value. When you design, when you do some layout, you get some approximate value. The precise value could be hugely off from the value you designed for, right. So, as far as agility is concerned, VCO is good, but as far as the spectral purity is concerned, as far as the accuracy is concerned, the quartz crystal is what I want. So, I need a way, I need a technique to combine these two. Now, as part of my plan, the first step is to study something called phase locked loops. So, the idea for a phase locked loop is there a way I can mimic the oscillation of a quartz crystal of a reference frequency, we are going to call it the quartz crystal reference frequency. So, I have a reference oscillator, I want to mimic this reference oscillator with an oscillator on chip. So, this is part of my plan, and to do that I need to build a control system that tracks the phase of the reference oscillator. Remember, the noise is in the phase noise. So, I need to track the phase of the reference oscillator and I need to build a control system that drives my VCO. VCO is the plant. Okay. And the phase of the VCO, the output of the VCO is an oscillation, the phase of that oscillation should mimic the reference phase. So, I need a feedback system. Okay. So, the control system is going to compare the reference phase with the phase of the VCO and it is going to control the plant is a VCO, right. So, this is the control system that I want to build. This control system is called a phase locked loop. This whole thing, this whole scheme of things is called a phase locked loop. Now, let us start understanding a few things over here. The first thing to understand is the property of phi ref, phi ref. So, this phi ref is what does it look like? It is the phase of the reference oscillator. Now, the reference oscillator is always oscillating. It is the crystal oscillator, the quartz crystal. So, the reference oscillator is always oscillating in this fashion, and its phase, that is the input to my control system. What is its phase going to look like? So, let us say that, let us assume that the phase at this point of time is equal to 0 degrees. Let us assume, we have to start from somewhere. So, let us say that at that point of time the phase is 0 degrees. So, at this point of time the phase is going to be 360 degrees, or rather 2 pi, and then you can conceive of the phase going linearly as a function of time. At this point of time it is 4 pi, over here it is 2 pi, over here it is pi, and so on and so forth, 6 pi, 8 pi, and so on and so forth. You could also think of it as a sawtooth waveform, but that is too complicated, it is not necessary. I mean 2 pi, an angle between 2 pi and 4 pi is the same as an angle between 0 and 2 pi. So, you do not have to think of it as a sawtooth waveform, you can think of it as a ramp. So, that is the key word over here. This phi ref looks like a ramp. Now, if you have studied control theory, have you studied control theory? I am sure you have studied control theory in your undergraduate to some extent, something you must have studied, right. This is a core topic as far as electrical engineering is concerned. So, if you remember your control system, there are different varieties of control systems: position control system, velocity control system, right. So, just you have the arm of a tank, you are a tank over here. Okay. And your target is over here. So, you have to control the angle of your tank gun, so that it points accurately to the target. If your angle is off by even little bit, then your tank is going to not hit the target, right. So, here you are controlling the angle, or rather you are controlling the position of the tank gun. So, this is a position control system. Now, think of the following, that this target is moving. This target is not a static target. So, this target is hovering around between here and here, and you have to point your gun in a way that tracks the movement of your target. You have to keep tracking the position of your target. So, this is a velocity control system. Your tank gun has to oscillate, has to move around between these 2 points and accurately track the position of the target. Okay. Maybe your target is not oscillating like that, maybe your target is just moving from one point to another, in which case once again your tank gun has to follow the precise position of the target. Okay. So, this is called a velocity control system. Now, as far as we are concerned, the input that we are trying to track over here is continuously changing, it is a ramp. Okay. The control system that we have to build has got to be a velocity control system. All right. So, this is an important property of the control system that you have got to build. Fine. So, with this background, let us try to build something. What is a velocity control system? What is a velocity control system? You do not remember? Okay, we will come to it. Let me give you a feeler. I do not want to be teaching control theory here, but let me just give you a feeler of what we are talking about. Suppose the input is a step, going from 0 to 1. Okay, that is not the characteristics of our input, but suppose it is. In any case, this particular control system has a gain. This is the input, this is my output, the gain output by input equal to 1 A by 1 plus A, open loop gain divided by 1 loop gain divided by 1 plus 1 minus the loop gain. I am sorry, the open loop gain divided by 1 minus the closed loop gain. Right. This is the output by input for this particular system. Now, if your input is going from 0 to 1 and you have got A equal to 5, say A is 5. In that case, when the input is going from 0 to 1, if input is 1, then the output is 5 by 6, and that is no good, because your tank gun has to precisely point at the target and it can't be off by a fraction of a degree even. Make A large. If A is 1000, high gain amplifier, even then the output is 1000 by 1001, which is not good, because the tank gun has to point perfectly at the target, not almost at the target. Okay. So, however high the gain of your high gain amplifier is, it is not going to do a good job. So, what do we do? Now, next step, suppose you put an integrator. Okay. Basically, you integrate the error signal. If the error signal is anything but 0, then the integral of the error as a function of time is going to be infinitely large. Infinitely large means that the output is going to be infinitely large. It is inconceivable, therefore, the error signal has got to be 0. So, that is the hypothesis. Let us see how we analyze this. The integrator has a transfer function of 1 by s. Okay. Transfer function of 1 by s means that the open loop gain as well as the open loop gain is a by s. That means that my output by input is a by s divided by 1 plus a by s, which is equal to a by s plus a, which is equal to 1 by 1 plus s by a. Okay. So, this is the transfer function. Your input, what is your input? U of t. Laplace transform of the input is 1 by s. So, if your input is 1 by s, your transfer function is 1 by 1 plus s by a, then the response is going to be 1 by s times 1 by 1 plus s by a. Okay. Let us say this is x of t, this is y of t. So, y of s is 1 by s times 1 by 1 plus s by a, and you can break it up into partial fractions. If you break it up into partial fractions, you are going to get k by s plus k 1 by s plus k 2 by 1 plus s by a. Okay. Now, as time t tends to infinity, okay, let's do the partial fraction breakup. If I multiply both of these by s, then I am going to get 1 by 1 plus s by a is equal to k 1 plus k 2 by 1 plus s by a. Okay. Now, if I plug in s equal to 0, then I have got k 1 plus k 2 is equal to 1. Okay. Next thing is multiply both sides by 1 plus s by a, and you have got 1 by s is equal to k 2 plus no, I am sorry. Okay. And now plug in s equal to minus a. If s is equal to minus a, then the second term goes to 0 and k 2 is equal to minus 1 by a. Okay, that is your partial fraction breakup. Now, what does this mean? This means that the response is equal to u of t and what is 1 by s plus a? This is equal to u of t times e power minus t by tau. All right. So, as time t tends to infinity, I get 1 and I get 0, which means I get exactly equal to 1. So, as time t tends to infinity, the output of this position control system, this is a position control system, is precisely equal to the input. So, this is what you are going to see at the output. This is a long analysis for something so simple, but hey, you need to understand what is going on. Now, if my input is not 1 by s, if my input is unfortunately 1 by s squared, that is a ramp, right, then what you are going to find is that a position control system will give you an offset. Let us just check for that. If your input x of s is equal to 1 by s squared, then the output is going to be equal to 1 by s squared times 1 by 1 plus s by a. Okay. And if you want to do partial fractions for this, this is going to be equal to k 1 by s squared plus k 2 by s plus k 3 by 1 plus s by a, and you can work out k 1, k 2 and k 3. What you are going to find out is that all three of these are going to be non-zero, all right. All three are going to be non-zero, which means hopefully k 1 is going to be equal to 1. Hopefully k 1 is going to be equal to 1. I am not going to do the mathematics here, but what you are going to see is 1 by s squared plus k 2 by s plus k 3 by 1 plus s by a. Now, k 3 by 1 plus s by a as time t tends to infinity is going to boil down to 0. Okay. K 2 by s is going to be k 2 times u of t. As time t tends to infinity, it is going to be equal to k 2, and 1 by s squared is the ramp that you want to track. So, what is the result? As time t tends to infinity, this term will drop out to 0, the second term will be a value equal to k 2, which means that there is an error, there is going to be a constant error of value equal to k 2. Okay, of course, you do the partial fraction breakup properly, you will get the exact value of k 2. What I am saying over here is that k 2 is not going to be equal to 0, definitely not. You are going to find out. Okay, do this as your homework exercise, prove to yourself. So, what this means is that if I make a trivial control system, a position control system, and the input is not a position, the input is a ramp, then the output is no longer going to be able to track the input. It is going to kind of do it with an error, there is going to be a lag. What does this mean for us? Our control system over here is trying to do velocity control. Here the input is constantly changing, the input is a ramp, and that means I can't build a simple position control system with one integrator over here, right. This is what we are trying to get at. Okay. All right. So, let us get back to our point of business. So, I have got a reference phase and I have got a plant, the plant is the VCO, it is generating an output phase in response to a control voltage. Now, we did not study the VCO like this, did we? No. We said that the VCO generates a certain frequency of oscillation in response to a certain voltage. So, when we studied the voltage controlled oscillator, we said that if I plot control voltage on the x axis, then the oscillation frequency will have some characteristics, something like this, probably other way around, it does not really matter. Okay. So, the frequency is a function of the voltage, not really the phase. Let us say, let us arbitrarily say that our VCO does not look like this, our VCO looks like this, does not really matter, but hey, let us say it is a linear function of the voltage, of the control voltage. Okay. In that case, what is the phase? It is not difficult to understand that the phase is the integral of the frequency. The phase at a time capital T is equal to the integral of the angular frequency starting from 0, let us say the reference the phase at time t equal to 0 is 0 to the current point of time, that is the phase, which means that phi of s is going to look like this. Now, I am saying that this omega of s, let us assume that omega of s is equal to some constant k times V control, okay, which means that omega of s is equal to k times V of s. That means that this particular plant, the VCO, can be modeled as something that is of this nature. Okay. What are the dimensions of k? So, here you have radians per second, here you have volts. So, units of k are radians per seconds per volt. So, that is the kind of plant that I am trying to control. The plant itself is some kind of an integrator, right. This is something that I need to understand. The plant is by itself something that behaves like an integrator. So, I have got an integrator built in to my plant, wonderful. Now, a typical control system, you need to compare the output with what you have got, the reference, you have to compare the reference, that is the input, with the output. So, your target is phi ref should be equal to phi out, or rather phi out should be equal to phi ref, that is what you want, right. So, you compare the two and you create an error signal. So, you want to compare the phase of the reference oscillator, the quartz crystal, with the phase of your VCO. So, this is called a phase detector. This is not an ordinary subtraction, right. This is no ordinary subtraction. You are comparing the phase of the reference signal with the phase of your output. This is not the voltage of the quartz crystal minus the voltage of the output. Be very careful about it, right. In response, you are creating a voltage, and then this has to go through some sort of a loop filter and generate V control. Now, the transitions between my control systems. So, I have first I have just a high gain amplifier, then to do position control I need to put in an integrator. If I want to do velocity control, I need to put in another integrator into the loop. Okay, that is basically the hunch, that you probably need to put another integrator. Now, unfortunately, if you do put in another integrator, strange things will happen to the loop will become unstable. Why? Why will the loop become unstable? Because the loop gain is going to be equal to A times minus A times 1 by S squared. You have got two integrators and A. So, your loop gain is minus A times 1 by S squared. The denominator of your total transfer function will be 1 plus the loop gain, which means I am sorry 1 minus the loop gain, which means that your denominator will contain something like 1 plus A. Let us just do it instead of trying to do it orally. if this is your system, then the denominator will have 1 plus a by s squared, which means that the denominator contains this, and this has 2 poles on the j omega axis. Where are the poles? All right. So, this kind of a system is not going to be stable. So, you can't put 2 integrators in the loop just like that. You have got to have a method over here. That is why you need to open your control theory book. All right. So, the general idea for our phase lock loop is this: I need a phase detector, then I need a loop filter, and then I have got my VCO, which is modeled as k by s. Okay. So, this is the general idea. Now, the first building block that I need is the phase detector. I am going to focus on that now, and we are going to do the loop filter in the next class. Hopefully I will be able to finish the phase detector today with the time that I have. Okay. Now, this particular phase detector, it is no ordinary subtraction that is going on. You have to understand first of all that what do the voltages look like? What does phi ref really look like? The reference input is a square wave, so digital square wave. What about the reference output? The I am sorry, not the reference output, the VCO output. The hope is that the VCO also generates a square wave, right? That is what you want to do. You want to get rid of amplitude noise, you want to reduce noise in your system. So, you want a square wave as the output of your VCO. Now, you might not get it, that is a different issue altogether, but the hope is that you are working with a square wave. So, let us try to work with a square wave. So, really I am not going to call this phi ref anymore, I am going to call this V ref. This is the voltage corresponding to phi ref, and the voltage corresponding to phi out is probably something like this as a function of time. And what is the objective? The objective is to find out the phase difference between the two. If phi ref is more than phi out, then you need to give a positive result. If phi out is more than phi ref, you need to give a negative result, right. That is the objective. You have got two digital signals. Is it possible to give a digital circuit that will give a digital output as to what the phase is. The inputs are digital, why can't the output be digital too? Circuit should be could completely be digital, conceivable, right? The inputs are already digital in nature. Is it possible? What do you think? What could be generating the phase difference between the two? When the two are same, when both are, all right, let us take a look over here. What is the output that you want? You want an output that is proportional to the time gap between these two edges. All right, an XOR gate, right? An XOR gate can do the job. Seems like an XOR gate can do the job. Let us just see if I do XOR of Vref and Vout. When Vref and Vout are different, it will give me a 1. When they are same, it will give me a 0. Okay. And if you take the average over a cycle, it is kind of proportional to the phase difference between the two. Think this works, right? It does not work. Why it does not work is that it makes no difference as to which side is positive, which side is negative, or whether you are doing Vref minus Vout, Vref minus Vout, or you are doing Vout minus Vref, makes no distinguish, it does not distinguish, right. So, as a result you get something which is proportional, the duration of the pulses are proportional to modulo Vref minus Vout. If Vref and Vout are out of phase by 180 degrees, then the output is always 1. Okay. So, that kind of tells you that on the average, if Vref minus Vout is 1 radian, then the output is going to be VDD by pi. So, pi radians gives VDD, 1 radian will give VDD by pi. But of course, the characteristics of the phase detector is like this. Okay. So, this is what an XOR operation will do. I do not want this. This is not good, it is not really, this is what I wanted, something of this nature is what I wanted, not this modulo. It is not what I want. It is okay, it will kind of work when the system is biased at this point. When the system is biased at that point, I will get correct results, but I want to be over here, I want 0 phase, right. So, in general, if you do use an XOR gate as a phase detector, you can use it. You are going to find that the loop locks at a phase difference of pi by 2 or minus pi by 2. Okay. So, this is something that you will observe. We do not want to make such a phase detector. So, it kind of works, not quite. Let us again see what I want. First of all, I should not be caring about both edges. I mean, the duty cycle of my 2 clocks could be different. So, it is unreasonable to compare both rising and falling edges, right. So, that is also something that you have to keep in mind, that you do not necessarily want to compare both rising as well as the falling edge. So, this is what I want. Let us modify my V out a little bit. So, if Vref is ahead of V out, or rather if phi ref is more than phi out, then my desired output should be positive. During that duration. If phi ref is lagging behind phi out, then my pulse should be negative during that duration. So, this is the kind of output that I want from my digital system. So, your system has 3 outputs, 3 possible levels. It should have a 0, it should have a plus 1, it should have a minus 1, which means that you need at least 2 binary digits to represent the output code. You need 2 binary digits, you can't do it with 1 digit. With 1 digit you can do only 0 and 1, you need 0, 1 and minus 1. So, you need 2 binary digits to represent the output. This is observation number 1. Observation number 2 is that you do not want combinational logic over here, you do not want to work at the, you want to ignore all of this. Okay, which kind of means that you need to build some sort of sequential logic. If you want to build sequential logic, you have to start with a state machine diagram. So, let us try to build a state diagram for this kind of a system. So, I am going to start with the 0 state, and when I am at the 0 state, this is my 0 state. If there is a rising edge on Vref, then I want to output plus 1. This is the state when the output is plus 1. And then as soon as a rising edge of V out comes, I want to go back to the 0 state. All right. Again, when Vref rising edge comes, I will generate plus 1, V out rising edge comes, I will generate minus 1, I will go back to 0. Now, while I am in 0, if a rising edge comes for V out, then I want to generate a minus 1. And then after that, while I am in the minus 1 state, if the rising edge for Vref comes, I want to return back to the 0 state. So, this is the state diagram of the phase detector. It is a kind of strange digital system. The events over here are the rising edges of Vref and V out. Those are the events. Okay. There are 3 states. The inputs are basically the rising edges of Vref and V out. It is a strange kind of a state diagram. Now, 3 states means you need 2 flip flops to build the system. Okay. And what I am going to do is, I am going to just go ahead and draw the system. It is not terribly straightforward to design it from scratch. So, and it is going to take a lot of time. So, I am just going to go ahead and draw it. So, at the rising edge of Vref, Q becomes equal to 1. Okay. This is the code for plus 1. And then at the rising edge of V out, this Q is going to be equal to 1, but I do not want the 1 to remain. As soon as such an event happens, I want to clear both of the flip flops as soon as both the outputs are 1. Then again, if V out goes high, then this particular output becomes equal to 1, that is the code for minus 1, and as soon as that happens, my output is minus 1. Then if Vref comes, plus 1 becomes high, and as soon as that happens, clear is activated and both signals become 0. So, this is the kind of circuit that our phase detector is, and this is what is used all the time. So, small bits of variations here and there. This is what is my phase detector. This is the final circuit. You have to remember that these flip flops need to be designed, the clear etc. Maybe it is clear bar, in which case you have to make a NAND gate. All those considerations you have to keep in mind. This is what is used in most phase lock loops. All right, we are going to stop here, and in the next class we are going to continue with the next important block that we have got over here, that is the loop filter. Okay, thank you.